All right, let's look at an example. We're going to apply this Taylor series formula that we derived to actually find a power series for a function. And so let's look at the function f of x equals e to the x. And our Taylor series formula says that this should be given by the sum from n equals 0 to infinity of the nth derivative of f evaluated at our center point. And I'm going to use the center point of 0 here, divided by n factorial times x minus the center point raised to the n. All right, so here we're using c equals 0 for our Taylor series, which means you could call this a Maclaurin series if you would like. And so we need to actually figure out what that formula looks like. Okay, so with our function f of x, let's first compute some derivatives. F prime of x, notice, is e to the x. And f double prime of x would be equal to the derivative of f prime, which is also e to the x. And that's going to be true of every subsequent derivative. And so when I compute the nth derivative evaluated at 0, notice that's just going to be e to the 0, which is 1. Okay, so we've got all of our derivatives evaluated at our center point figured out. They're all just 1. That's convenient. So let's now write down what these terms look like. When we plug in n equals 0, we'll have the nth derivative, which is just 1, all over 0 factorial times x to the 0. And then our next term will be, still our nth derivative is 1 over 1 factorial times x to the 1 plus 1 over 2 factorial times x squared plus 1 over 3 factorial over x to the n, or x cubed, excuse me. And that pattern is going to go on forever. And so we could also write this more concisely as just the sum of x to the n over n factorial from n equals 0 to infinity. All right, that is a power series for e to the x. And let's actually take a closer look at that with the help of Desmos. All right, so I'm going to graph the function e to the x. And let me back off there. And let's write down our power series, x to the n over n factorial. And notice if I use just one term, that would be just using, if I could go from 0 to 1, I will have, quickly shift back to our formula we derived. If we look at that circled formula, that's just the first term is x to the 0 is just 1, and 0 factorial we said is 1. I know that's a little counterintuitive, but that is actually how 0 factorial is defined. So we have actually just 1 plus the next term would be x plus x squared over 2 plus x cubed over 3 factorial, which is 6, and so on. And so if I just take the terms up to n equals 1, that would be a line, 1 plus x, and we'll see from our graph that that is just the tangent line. Okay? So if you use the Taylor series, but you only include all the terms up to the x equals, or to the first power, you'll get a tangent line. If you add one more, now we have a parabola. And as we add more terms, you'll see that it seems like we're doing a better and better job of matching the function. And let me zoom out just a little bit, and we'll see what happens as we add more and more terms. Oop, it's going a little too fast. All right, so Desmos seems to be struggling with this calculation here, but as I add more terms, you'll notice that the red curve, which represents our power series, stays closer and closer to the function e to the x. And it seems like it stays closer over a wider range. And so what that might suggest is that this series converges over at the very least a very wide range of x values. But we know how to check for the radius of convergence, so let's do that. Let's actually figure out where this series converges to e to the x. And so we've got our power series formula right there, x to the n over n factorial. Where does the sum from n equals 0 to infinity of x to the n over n factorial converge to e to the x? Well, let's try to find our interval of convergence. We can use the ratio test for that. So the ratio rho is the limit as n goes to infinity of the absolute value of the next term over the current term, or multiplied by the reciprocal of the current term. And if you remember, well, x to the n will cancel with n of the factors of x up top, and we'll be left with just an x. And n factorial will cancel out some of the factors in the bottom, because n plus 1 factorial is just n plus 1 times n minus 1 times n minus 2, and so on, or n plus 1 times n factorial. And so we will be left with the limit as n goes to infinity of the absolute value of x on top. There was one x that survived. And on bottom, we'll just have an n plus 1. And I guess I don't need absolute values in the denominator because n plus 1 is already positive. And notice it does not matter what x is. The denominator is going to infinity. The numerator is staying the same size because x is independent of n. And so this is always going to be 0. And so the conclusion is this series always converges by that I mean for all x, because the ratio was always less than 1. Okay? If the ratio is always less than 1, then we know that the series converges. And so the radius of convergence is infinite in this particular case. Awesome. Well, that is kind of nice. We now know that this series converges to e to the x. And that's a really powerful idea, because now we can find out what a whole bunch of other series that are related to it converge to. So for example, one of the series that we studied earlier, we did some example problems like this, looked like the sum from n equals 0 to infinity of 1 over n factorial, right? That's a series. Now, you could try to use a bunch of your tests to determine if this converges or not, and you'll see that since n factorial goes to 0 really, really fast, a comparison test, for example, will show you that it converges. But the Taylor series tells us not only that it converges, but it tells us exactly what it converges to. Because notice, that's the same thing as the sum from n equals 0 to infinity of 1 to the n over n factorial, since, of course, multiplying by 1 n times is no different than multiplying by 1 time. That doesn't change anything. And we already know that x to the n over n factorial converges to e to the x. And so this must converge to e to the 1. All right, and we can check that. Go back to our Desmos calculator, and I'm going to copy this, and I'm just going to put in a 1 on top. All right, and notice if I just use the 0th term, I get, or the first two terms I get 2, but as I increase the number of terms, what does it look like the sum is approaching? 2.718, which is approximately e. And if I change the problem slightly, what if I instead use an alternating series? What does that converge to? Well, notice that is just the same series where we plugged in -1 instead of 1. And so that must converge to e to the -1, or 1 over e. And we could do this for any value of x. So you put a 2 to the n in the numerator, it's going to converge to e squared. You plug a -2 in, it's going to converge to e to the -2, and so on. Okay, so Taylor series. They allow us to represent functions as a power series. We find the representation by computing all of the derivatives and plugging in the center point. We can check the interval of convergence of that series, and once we've shown where it converges, then we can start to plug in particular values of x and find formulas to sum a whole bunch of different series. We'll look at some more examples like this in the next video.